In this video, we are going to be dealing with the topics of chapter 20, which have to do with carboxylic acids and their derivatives. First, we are going to be introducing what is a carboxylic acid. Now, carboxylic acids are going to be organic compounds that have the functional group of carbon double bonded to oxygen, and that carbonyl is going to be attached to an OH group. Overall, this motif, which I am putting around dotted lines, is known as a carboxyl group because in essence we have a carbonyl plus a hydroxyl group. Now, carboxylic acids are abundant in nature and found in a wide variety of synthetic pharmaceuticals. So, for example, acetic acid is the molecule that is responsible for the pungent smell in vinegar. Butanoic acid is responsible for the rancid odor in sour butter. Now, in dirty socks, the molecule that it is detected in your nose is hexanoic acid. And lastly, just to talk about one more, the molecule that is responsible for the sour taste in milk is lactic acid. Now, you can see in the bottom of the molecule, we have a series of medications that are actually utilized in order to treat different conditions, and they all contain this carboxylic acid motif. So, when it comes to a carboxylic acid, understand that the ending of a carboxylic acid is oic acid. So, when we are trying to name a carboxylic acid, understand that we're going to, as usual, find the longest continuous carbon chain. Now, as it says in the bullet point, the carbon of the carboxylic acid, meaning the carbon that is double bonded with oxygen, is going to be assigned a locant of 1. So the priority in the numbering is going to be the carbon atom that is double bonded to oxygen and single bonded to DOH. So if I designate the numbering for carboxylic acid, this is carbon 1, carbon 2, 3, 4. In essence, you can write the alkane name for it. And then what you're going to proceed is to erase the E in the alkane name and include the ending oic acid. And that's where the name butanoic acid comes from. When we have, as you can see, the carboxylic acid on the right, we're going to find the longest carbon chain. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Remember that when we are numbering, we only number the carbon atoms. Now, in our longest carbon chain, we have 5 atoms. That's where the word pentanoic acid comes from. Then we are going to have specifically for this molecule 2 substituents, methyls on carbon 4, and in this case we also have a hydroxyl group. Now, understand that when it comes to this, if you have in a molecule a hydroxyl group compared to a carboxylic acid, the carboxylic acid is going to get priority. So, after the numbering has occurred for our substituents, I'm going to highlight now the hydroxyl group. Understand that the same rules that we have explored previously apply. You're going to put the substituents as a prefix of the longest parent chain name, and they have to be there in alphabetical order. The names and numbers have to be separated by an hyphen. If numbers have to be written consecutively, they will be divided by a comma. So when we are alphabetizing this, remember, we are comparing the H to the M in the methyl because the prefix that it is utilized to signify that we have more than one of the same substituent, does not get alphabetized. So the correct name for that molecule is 5-hydroxy 4,4-dimethyl pentanoic acid. We can also have carboxylic acids where the group is outside a ring system. And when a carboxylic acid group is attached to a ring, it is named as an alkane carboxylic acid. So as you can see in the molecule that we have in the top right corner of the slide, we are going to use as the parent chain the word carboxylic acid to represent that we have a carboxylic acid outside of that ring system. And as a prefix of that, we are going to put the name of the cyclic alkane. So this ring system that I highlighted in orange is called cyclohexane. So the correct name for this molecule is cyclohexane carboxylic acid. There are also many common names for carboxylic acid, and it depends on the number of carbons that we have in the system. You should be familiar with at least the 5 that are presented in the slide, which include formic acid, which is the simplest carboxylic acid, which has 1 carbon atom. So if you were going to do the IUPAC name for formic acid, it would be methanoic acid, because there's only 1 carbon in the system. As you can see, we have acetic acid, which the IUPAC name for it will be ethanoic acid. We have propionic acid, which the IUPAC name will be propanoic acid. We have butyric acid, which the IUPAC name will be butanoic acid. And lastly, one that it is very important that is part of the aromatic system is benzoic acid. And this is where we have a benzene ring attached to that C double bond OH. Now, in one molecule, we can also have 2 carboxylic acid present. So understand that when we have a dicarboxylic acid, they are named with the suffix diiotic acid. So for example, the molecule that we have in the corner, if we number the carbon atoms, there is 1, 2, 3, 4, 5. And I decided to number it from right to left, just because in this molecule it doesn't matter. There's no other substituent attached to it. If there were other substituent, then the numbering would not proceed in this way. But you can imagine that you could also number it 1 through 5 going from left to right. So as you can see here, because we have a dicarboxylic acid, we write the alkane name, pentane, to signify that we have 5 carbon atoms. And those 5 carbon atoms, again, carbon 1 and carbon 5 are the ones that contain the C double bond OH. We have 2, that's why the di meaning 2, and then iotic or oic acid means that there's 2 carboxylic acids. Now, understand that some dicarboxylic acids actually have common names. So as you can see in the list that we have here, this is oxalic acid, malonic acid, succinic acid, and glutaric acid. When we look at the structure of carboxylic acid, remember that carboxylic acids, because the carbon atom is attached to a double bonded oxygen, that carbon atom is trigonal planar in its molecular geometry. One of the important things to remember about carboxylic acids is that they can actually undergo interactions with themselves. They can have hydrogen bonding events, but understand that when you have a carboxylic acid solution, one of the important things that have been observed is that these hydrogen bonding events create what are called dimers, meaning that we're going to have a hydrogen bonding event between the OH of a carboxylic acid and the oxygen in the C double bond O. And as you can see, we can have two of them if we're looking at a pair of carboxylic acids interacting with each other. As a result of this, carboxylic acids have a higher boiling point than alcohol, but again, it's because of the formation of this dimer that can occur between carboxylic acids. When it comes to their acidity, remember that carboxylic acids are weak acids. So since they are weak acids, they are able to donate a proton and they can exist as a carboxylate salt in the presence of base. Later, we're going to explore what is the benefit of actually having a carboxylate salt. So the reaction that we have here is just representing the acid-base reaction that carboxylic acids can undergo. Now, when we have a carboxylate ion for carboxylic acid or a carboxylate salt, understand that we can actually name those ions. All we have to do is remove the ic acid ending of our carboxylic acid name and replace it by the ending ATE. So as you can see here, the carboxylate salt of benzoic acid is known as sodium benzoate. In the beginning, as you can see, we're going to add the word of the metal because it can be paired with any cation, sodium, lithium, potassium, anybody from 1A or even 2A. But understand that most commonly when these reactions are occurring, we are using strong bases that are coming from hydroxides and metals in group 1A in the periodic table. So, when we put a carboxylic acid in water, understand that they only dissociate slightly. Again, because carboxylic acids are weak acids. So when we have a carboxylic acid, as you can see, and we put it in water, one of the reactions that we can see is that the water is going to deprotonate the carboxylic acid and make that carboxylate ion that was mentioned in the previous slide. Now, understand that this is not favorable because when we are doing this acid-base reaction, what we're forming is that carboxylate ion and hydronium. And this hydronium ion, because of its acidity, when compared to the carboxylic acid, it actually pushes our equilibrium towards reactant. So that's why we observe that the arrow, which I'm highlighting in gray, is actually towards the reactant. Most carboxylic acids actually have a pKa around 4 to 5, and understand that in a way represents something that is pretty acidic, but it is still a weak acid. Now, when we compare these carboxylic acids to HCl, okay, to hydrochloric acid, or even H2SO4, sulfuric acid, they are very weak. Remember that HCl along with sulfuric acid perchloric acid, nitric acid are strong acids. They're going to have pKa's that are actually in the negative. Now, if we compare a carboxylic acid to an alcohol, they're actually relatively acidic, because remember that the pKa for an alcohol is specifically around 16, and again for a carboxylic acid is around 4. So what does this imply? That when we have a carboxylic acid, they are going to be more willing, okay, to lose the proton that I'm circling in the dotted line compared to the alcohol. So again, if we compare it to a strong acid, they're going to be weak. If we compare it to an alcohol, they're going to be better acids than alcohols. Okay? If we think about it, where does the stabilization of that carboxylate ion that was created comes from? It is a resonance stabilization. Once that proton leaves the carboxylic acid, one of the things is that those electrons that are now in that negative oxygen can resonate and be shared between the two carbon-oxygen bonds. So this creates a molecule that now it can be resonance stabilized. Now, understand that if we have electron-withdrawing substituents attached to the alpha carbon on a carboxylic acid, they are going to affect the pH. The pKa. So, if we compare the pKa of a carboxylic acid with molecules that are similar structurally in terms of having carbons and oxygen atoms, and the difference between the molecule that we have in the left and the molecules in the same row is the addition of those electron withdrawing substituents and as you can see, as we increase the number of electron withdrawing substituents, then the acidity or in terms of pKa is going to be the willingness to dissociate that proton is going to be greater, because we see a value of pKa that it is decreasing. And if we rationalize it, why that is because remember that once that proton leaves, we are going to create a carboxylate anion. Having an electron withdrawing group, what it's doing is actually inductively pulling electron density away from specifically this area of the molecule in any of them. So it's going to be pulling electron density towards the electronegative atom. And overall, what happens is that electron density that it is fluctuating between the carbon-oxygen bonds, inductively, the chlorines in this case is going to be pulling it towards them and stabilizing them. That's why we see the decrease in the pKa, because once that proton leaves, we're going to have an ion that it is stabilized. That being said, understand that as I mentioned to you, those chlorines need to be at the alpha position, which is the carbon that is immediately attached to the C double bond O, as you can see also in the illustrations. So understand that the greater effect is going to happen when our electron withdrawing group are at the alpha position. If we compare the presence of electron withdrawing groups at the beta position or at the gamma position. So if we look at and number the carbon atoms, this is 1, 2, 3. So this is 2 carbons away from C double bond O. This is 3 carbons, 1, 2, 3, 4, 3 carbons away from the C double bond O. Let me illustrate that where I get that number of 2 or 3. So 1 carbon away, 2 carbons away. That's what the beta position is. The gamma position is, again, if our starting point is the C double bond O, that's 1 carbon away, 2 carbons away, 3 carbons away. That's where the gamma position is. As you can see is, as that electron withdrawing group is more separated from our C double bond O, the effects are not going to be as greater as being close to the C double bond O in terms of the pKa. When it comes to the electron withdrawing group effects, as you can see, they can happen specifically also at the level of the benzoic acid. So as you can see, electron withdrawing groups substituents affect benzoic acid as well. So for example, as you can see, if we compare different groups, like a nitro group versus an aldehyde, so this is a nitro group, this is an aldehyde, versus a chloro group versus just having a hydrogen, a methyl group, or even a hydroxyl group. Remember that our starting point for benzoic acid will be here. This is where we have benzoic acid. So, as you can see, this electron group specifically is going to be para specifically to our C double bond O motif within the ring. So the atoms that you see, or the group of atoms that you see to the left of this chart, meaning the nitro, the aldehyde, or even the chloro group, are going to, as you can see, reduce the pKa because they are more electron withdrawing as we move towards the nitro. If we move and we compare it to the methyl and the OH, as you can see, the effects in terms of the acidity are not going to be as great. It will still be acidic, but it's not that it's going to make it more acidic. It's just going to leave it, pretty close to, a carboxylic acid pKa. And that's because when we're looking at methyl and hydroxyl, remember, those are electron donating groups. So, there are many reactions for the preparation of carboxylic acids. And here we have a review of some of the reactions that make carboxylic acids that have been discussed in previous chapters. As you can see, the first one that is illustrated here in the slide is the oxidative cleavage of alkynes. So alkynes, when they undergo ozonolysis, as you can see, they can produce carboxylic acids. We can oxidize primary alcohols with a strong oxidant like chromic acid. So these reagents are the same thing as saying H2CrO4 that also produces a carboxylic acid. Specifically oxidation of alkyl benzenes, okay? So if you have a benzylic proton, again, utilizing chromic acid, they can also produce a carboxylic acid, but it's going to be specifically benzoic acid. So these are 3 reactions for methods to produce carboxylic acids. Now, there are 2 more reactions that were learned in here that produce carboxylic acids. And one is the hydrolysis of nitriles. As you can see, if you have a CN group in a molecule, when we put it with hydronium and heat, that produces a carboxylic acid. So as you can see, this can allow for a 2-step synthesis of a carboxylic acid taking into account that if we start with an alkyl halide, and as you can see, this is a primary alkyl halide, this reaction can undergo an SN2 reaction or a substitution reaction. Once that is present, then we can make the carboxylic acid of interest. One other reaction that you guys need to be familiar with will be the carboxylation of a Grignard reagent with CO2. So if you have a Grignard reagent and you expose it to CO2, as you can see in step 1 of the reaction, you're going to take the Grignard, react it with the CO2 in the second step of the reaction. Then the carboxylate that was generated from the first step can be protonated to create the carboxylic acid. Okay, so understand that that second step, that acidic workup, is necessary with any of these reactions, because that's what's going to protonate specifically our carboxylate ion and produce the carboxylic acid. Now, as you can see, this provides a particular method to make a carboxylic acid. So the reaction that we have illustrated here, we have phenyl Grignard that is reacted with CO2 followed by acidic workup. As I talked about in the previous slide, understand that this is a two-step process, because as you guys hopefully remember, when we have acid in the presence of a Grignard, that destroys Grignard. So that's why when you're writing these steps in order to illustrate the formation of a carboxylic acid by reacting a Grignard with CO2, you need to put it as step 1, and then step 2, the acidic workup is going to be independent from the addition of that CO2. So as you can see in this reaction, we're illustrating a new way to make, specifically here in the target, benzoic acid. But you can utilize it to make any organic compound. Now, carboxylic acids, understand that they can be reduced to primary alcohols, but we need a strong reducing reagent. And the only way that we can accomplish that is by using lithium aluminum hydride followed by an acidic workup. So with that, we are going to take our carboxylic acid to a primary alcohol. Now, understand that in essence what is happening is that since lithium aluminum hydride is a strong base, okay, it can deprotonate the carboxylic acid first. So as you can see here, what is being illustrated is that the lithium aluminum hydride is going to deprotonate the carboxylic acid, and we're going to be forming a carboxylate salts, okay, along with aluminum trihydride, and we're going to be also making hydrogen gas, so molecular hydrogen. In the next step of the reaction, as you can see, that ALH3 is going to create specifically the protonation of the carbon in the carbonyl. The oxygen in that carboxylate is going to be coordinated with the aluminum, okay? And in the next step of the reaction, the electrons from the oxygen are going to come down and is going to kick out this group, the oxygen that was coordinated with the ALH2. So at first, in this process, in this mechanism, understand that we produce the aldehyde. But as we learned previously, aldehydes in this case are just going to be specifically an intermediate. This intermediate is going to be short-lived because in the presence of lithium aluminum hydride, as previously you guys have learned, aldehydes also proceed to make a primary alcohol. So again, here the aldehyde is not kept, it is an intermediate. So in the next step of the reaction, that aldehyde that was produced is going to be reduced to the primary alcohol through a series of steps that in this case that ALH4 is going to specifically attack the carbon and the carbonyl. The electrons are going to go up to the oxygen in the last step of the reaction. As you can see, this is the acidic workup, or step 2 in the reaction. We are protonating our molecule to make the primary alcohol, which is the overall result of the whole process. Understand that another reaction for carboxylic acids is that BH3 can be used instead of lithium aluminum hydride and is chemoselective for carboxylic acid. Now, understand that in this process, so we can utilize it if we have a dual functionality in a molecule and we only want to reduce the carboxylic acid. So if we look at the bottom molecule, we have two functionalities. We have a ketone and we have a carboxylic acid. Now, if we propose that in this molecule we were going to get to the alcohol via lithium aluminum hydride, it wouldn't work. And the reason is because ketones can also react with lithium aluminum hydride to, in this case, to selectively reduce the carboxylic acid. Then we can propose using BH3 with the solvent THF to take only reduce the carboxylic acid to the primary alcohol.